Hey class, Mr. Moydin here with a video on how to make a function differentiable. The key background knowledge to know for a problem like this is that a differentiable function means that it must therefore also be continuous. In other words, to be differentiable implies that it's also continuous. So the analogy that we've used for talking about differentiability is our old friend Mr. Picklecar, right? Or Mr. Frumble or whatever his name is. So for him to drive over a curve, it has to be smooth, it can't have any holes or breaks in it, but it also can't have any sharp turns. So continuity is a prerequisite. It has to be free of holes or asymptotes or jumps in order for a car to go across it, but it also has to have a smooth transition. So let's guarantee continuity first and then find the derivative. One other way to interpret this is that the derivative also has to be continuous. So the function and its derivative must both be continuous, and it's those two requirements that will make our two-variable equation here solvable. So let's go ahead and dive in. We're going to make sure that this thing is continuous. We're going to force continuity by plugging 2 essentially into both of our functions. So from the left, I'm going to plug in 2, and from the right, I'm going to use this function. I'm going to plug in 2 there. And of course, at exactly 2, it's one of the functions also, so those two should take care of themselves. So from the left of 2, I have a times 2 squared plus b times 2 plus 2, or 4a plus 2b plus 2. And from the right hand side, I have the other function, so that's negative 1/2 times 2 squared is, let's see, 2 squared minus 4 times 2 plus 1. So 2 squared is 4. Negative 1/2 times 4 is negative 2. Minus 4 times 2 is 8 plus 1. Negative 2 minus 8 is negative 10 plus 1 is negative 9. So from the right, this function, I get negative 9. From the left, I get this junk. So in order for it to be continuous, the left and the right have to equal each other, and so does the middle. But the middle, again, is one of the two functions anyway. So these two things need to be equal for this to be continuous. For it to be continuous, those two things, the left and the right there, have to equal each other. So I'm going to simplify this a bit. I'm going to have 4a plus 2b. If I take away 2 from both sides, I have 4a plus 2b equals negative 11. This relationship must be true in order to have a continuous function. However, there are two variables there, and there are many ways to solve, in fact, infinitely many ways to solve that equation. So in order to solve a two-variable equation, or system rather, you need another equation. And that's exactly where the idea of differentiability comes in, because the derivative must also be continuous. So I'm going to take the derivative. It's a piecewise function, so it's going to be a piecewise derivative. The power rule here will tell me that 2ax plus b is the derivative of the left piece, and that's valid when x is less than or equal to 2. Oops, ran out of room there. 2. And the right-hand derivative would be, using the power rule once again, negative x minus 4, and that's valid when x is greater than 2. So for this function to be differentiable, the derivative function, which is here in red, must be continuous, which means the left and the right and the middle have to be the same also. Again, the left and the middle are the same already, so that's not going to be an issue. All it is the left and the right. So plugging in 2 into our derivative function, we have 2a times 2 plus b, and that would be 4a plus b. That's the from the left, so that's our slope from the left, because the derivative, of course, is a slope. From the right, our slope is negative 2 minus 4, or negative 6. So our slope from the right-hand side is definitely negative 6. Let me make sure that's a 6 and not just a, don't want to get you confused with a b. So there's a slope from the right-hand side. Here's a slope from the left-hand side. For differentiability, these slopes must equal each other. So in order for our slopes to be a smooth transition, that has to be true. So we have two constraints, the two underlined shades of blue there. So they both need to be true at the same time. So that's where we're going to solve a simple linear system of equations. So let me choose a green color for this step. Both of these things need to be true. That 4a plus 2b needs to equal negative 11, but simultaneously 4a plus b needs to equal negative 6. Now there are several ways to approach a problem of this type. You may have noticed I'm a big fan of the elimination method, so I'm going to use that here. One reason I know that is because these are the same quantity, so if I subtract them, they'll eliminate each other. So I'm going to subtract the bottom function from the top function. So you got to be careful with your signs here a bit. 4, which is the top, minus the 4 on below, that's going to eliminate. 2 minus the 1 is just going to be 1b, just b. And negative 11 minus negative 6 really means negative 11 plus 6, which of course we know is negative 5. So boom, there's b. b is negative 5. And I've run out of room again, so I'm going to do this over here. b being negative 5 means that our other equation, which was 4a plus 2b equals negative 11, the same one as above, I can replace b with, of course, negative 5. So that's going to be 4a plus 2 times negative 5 equals negative 11. So this is going to be negative 10. I'm going to add 10 to both sides. So 4a equals, when you add 10, negative 1. Divide both sides by 4, and you get a equals negative 1/4. So in all this big chain of rules here, we have one constraint on a, another constraint on b. So a is negative 1/4, and b is negative 5. I graphed these to check. I don't have the graph visible here because the software doesn't let me do it, but it does make a smooth parabola composed of two pieces. Alrighty, hope this helps you out.